Hello, everybody, and welcome to this very first mini version of the Biomch-V online biomechanics lectures series. Today's lecture will be brought to you by Richard Baker. I'm Dan Bassett moderating, and I'll go ahead and pass the word directly to Richard.
Hi, everybody. This is primarily a trial run to demonstrate how the technology works, but I thought I'd give a little report on a recent research project we've finished that I think you all might be interested in. So the basic idea of us was to try and work out to what extent foot contact in human walking can be considered as a collision. Despite the early and widespread adoption of the term heel strike, the early pioneers stressed the importance of the foot making a controlled contact with the ground. I've gone and looked at the work of Saunders, Inman and Eberhardt, for example, and they never used the term heel strike as far as I can see. They only ever talked about foot contact. Then Jim Gage, in his third prerequisite for normal walking, specified it as pre-positioning of the foot in terminal swing, which presumably is as a requirement for a controlled contact. On the other hand, of course, there is a very substantial body of work that focuses on foot contact as a collision. If we look back to Jacqueline Perry's work, she defined 4 locomotor functions, with the third one being shock absorption, which clearly presupposes some shock to absorb. More recently, the dynamic walking group have made the collision a key component of their understanding of walking. And there's now over 40 articles citing the review article in which they most clearly outline this. The only experimental work I'm aware that's actually sought to look at this is the work from about 20 years ago of David Winter. He measured the horizontal and vertical components of velocity of a point on the heel, as you can see in these graphs here. And he came to the conclusion that the trajectory of the heel immediately prior to heel contact is virtually 0 in a vertical direction and is very low in a horizontal direction. And on the basis of this, he came to the conclusion that the use of the term heel strike is probably inappropriate. In fact, in a later work, he described 5 major motor tasks, of which the third was control of the foot trajectory to achieve safe ground clearance and a gentle heel or toe landing. So the question is, which is correct? Is the foot placed gently, or is there a collision? Now, in many ways, Winter's method looks appropriate. If the foot is virtually stationary before it contacts the floor, then it doesn't really seem logical to refer to that contact as a collision. However, if we look more closely at his data, it's not quite as conclusive as he claimed. The low velocity he recorded in a horizontal direction was about 0.9 meters per second, which corresponds to about 2/3 of walking speed, so it's clearly not 0. On the other hand, his paper lacks some key experimental detail. For example, there's no mention of any consideration of rotation of the foot about the ankle. And if the foot is rotating about the ankle, then the measurements will depend critically on exactly where the marker was placed on the foot. Another consideration is that there isn't any mention of any filtering of the data anywhere in the paper. In his other works, we know that David Winter filtered data quite heavily, and this would clearly have a significant effect on the velocity of a specific marker at a transitional point in the gait cycle, such as foot contact. So the aim of this study has been basically to repeat David Winter's work, but to pay attention to some of these experimental details and just try and confirm what the measurements actually are, and of course using modern measurement equipment. So we took a simple 6-degree of freedom cast type model and used it to track the hip, knee and ankle joint centers, and an additional marker on the placed as low as possible on the posterior heel without it being knocked off during walking. We then tracked the trajectory of those markers over the whole gait cycle, but taking it from foot off to foot off. And we time normalized this to 100 frames of data over that period. At the same time, we measured the ground reaction with our force plates, and we defined heel strike as occurring at the first instant when the measured vertical component of the ground reaction was greater than 10 newtons. And then we backtracked slightly so that we looked at the frame before that. So basically this is 1% of the gait cycle before contact is recorded. There wasn't any filtering of the data within the trial, and the smooth curves in the graphical output you'll see later are a consequence only of averaging across trials. We looked at 10 healthy adults. They were walking at 3 walking speeds, self-selected speed, and 25% faster and slower. And we measured 6 walks at each walking speed for each subject. But in order that we didn't get any artifacts due to gap filling, we only used those where we had complete marker trajectories throughout the gait cycle being considered. So looking at the results, the walking speeds were quite unremarkable. Self-selected speed was about 1.2 meters per second. But then if you look at the calculated heel velocities in the horizontal direction, you'll see at slow walking speed we were unable to measure any horizontal velocity at all. At self-selected walking speed we measured velocities of around about 4 centimeters per second. And even at the fast walking speeds, the velocity was only about 0.2 meters per second, which is about a quarter of that recorded by Winter. To put this in some sort of context, you can look at the velocity that the hip is traveling with at the same time. This is actually the point in the gait cycle when the hip is moving fastest. And you can see that even at fast walking, the heel is moving only at about 10% of the hip velocity, and it's closer to 2% at self-selected walking speed. As might be expected, you can see that the horizontal velocities of the knee and ankle take on intermediate values. Interestingly, the values are actually a little bit higher in the vertical direction, which is in contrast to Winter's observations that he felt the vertical velocity was virtually 0. The negative is that the marker is traveling a little bit downwards, which of course is what you might expect, and the values are all less than 20 centimeters a second. So the broad conclusion of this is that the data tends to support Winter's hypothesis, or his third motor task, that control of the foot trajectory is required to achieve a gentle heel or toe landing. There isn't any real evidence of anything that could be called a collision at all. We thus reach the conclusion that immediately before foot contact, the hip is moving forwards at about 1.6 meters per second, or at least it is at self-selected walking speed, but that the point on the heel that makes contact with the floor is actually close to stationary. And we can turn this on its head a little bit and hypothesize that the primary task of late swing is to decelerate the foot so that it's nearly stationary at the same time as the hip and, of course, the center of mass are progressing forwards at their maximum velocities. So what mechanisms are required to achieve this? Our measurements suggest that the knee is moving about 10% slower than the hip, suggesting that in late swing the hip is already beginning to extend a little. The ankle is moving considerably less quickly, about a third of the speed of the hip, suggesting that over 50% of the reduction in speed is coming from knee flexion, occurring in late swing. The ankle, however, isn't stationary. It's still moving forwards by about ½ meter per second, and plantar flexion at the ankle in late swing is also required to make sure that that point on the heel that's about to make contact with the floor is actually moving backwards with respect to the ankle as well. This understanding is confirmed on the graph of how hip, knee and ankle velocity varies through the gait cycle, plotted from toe off to toe off with the red line indicating foot contact. It can be seen that knee flexion and plantar flexion both start at about 8% of the gait cycle before foot contact. If we look very closely at the graph, we can see that there is a very small evidence of some hip extension, the dotted line, starting very late in swing just before toe off. Peak knee flexion velocity, however, peaks at about 100 degrees per second, almost exactly at foot contact, and continues at this value into early stance. The plantar flexion velocity, given by the dashed line here, is a little bit lower at the instance of floor contact, but increases a little in very early stance, presumably as a response to the action of the ground reaction. It should be noted that these angular velocities are additive. So at the frame before foot contact, the foot is rotating at about 200 degrees per second in relation to the ankle, which in itself is moving forwards at about 0.5 meters per second with respect to the floor. So matching the speed of a point on the heel to make contact with the floor at nearly zero velocity is a considerable challenge to motor control. It doesn't really surprise me, given this, how many people with neurological problems choose to avoid the requirement by walking on their toes. So, in conclusion, a gentle contact requires considerable knee flexion and plantar flexion velocities in late swing before foot contact. Knee flexion and plantar flexion are both starting in late swing. This isn't, of course, what you read in the textbooks, which almost all assume that these are responses to the ground reaction in early stance. A final thought to leave you with: if foot contact is such a gentle event, can stance phase knee flexion be a shock absorbing mechanism? It looks to me as if there isn't actually any shock to absorb, and it's interesting to think about what this mechanism might actually be for. But I'll leave that question for another time and be happy to hand back to Dan to manage any questions you've got.
Thank you, Richard. That was a very fascinating talk. In fact, I find it to be very interesting as it brings into question something that in clinical biomechanics we generally take as standard. And I would think that, especially for children who are having some neurological control or motor control issues, we can see how this impacts how we would help them achieve a more normal type of gait. So a question for you is, do you think that we can actually train children or adults, for that matter, to have more knee flexion in order to achieve a more appropriate heel strike? Or do you think the mechanism of training should be different in that?
Well, I think the first thing to acknowledge is that there may well be different ways of walking and managing the transition for stance from swing into stance. My feeling is that achieving a heel strike is a particularly challenging one for your motor control system. Actually landing on your toe gives you an extra degree of freedom, and I suspect you can cope with a higher contact velocity and compensate for it with toe walking than you can with heel walking, which is why children might choose to do so. Whether you can actually educate them to walk with this pattern is a lot less clear, and I think it's one thing we'd be very interested in trying. One of the things, of course, with the modern motion analysis systems that have got some capacity for biofeedback is that we could perhaps use the motion system as a way of feeding back just how much knee flexion they are achieving in early stance, and maybe helping them to encourage and to develop that. We have to remember that whatever we do isn't going to get around the motor control deficit, and actually accepting that the toe walking might be a better strategy for them is of course an alternative approach to managing the child.
Well, thank you very much. Really appreciate the live online lecture, and hope to see you at a future one as well. And thank you, everybody, for viewing.
Thank you very much.